At sunrise on October 24, 2023, Otis was a tropical storm south of Mexico. A day later, it was a Category 5 hurricane at Acapulco. The change was so fast that the storm seemed to become a different machine overnight. The evening satellite picture did not show a giant, perfect eye. It showed a compact storm still fighting wind shear and dry air. Forecasts expected strengthening, but not the leap that followed. The frightening part was not where Otis went. It was what Otis became. In 21 hours, its estimated maximum wind increased by 90 knots. That is more than 100 miles per hour of added wind speed. Deep thunderstorms wrapped around the center, the inner core closed, and a tiny eye appeared while the coast drew closer. Warm water gets most of the blame. The Pacific was unusually warm, between 30 and 31 degrees Celsius near the storm. But warm water by itself cannot explain the timing. Tropical oceans hold huge warm regions where most disturbances never become major hurricanes. So what changes when a storm goes from using the ocean to accelerating on it? Why can the same ingredients produce a messy tropical storm for hours, then suddenly organize into a rapidly strengthening hurricane? Meteorologists call this rapid intensification. The standard threshold is a wind increase of at least 30 knots in 24 hours. The threshold describes the result, not the mechanism. The mechanism lives inside a coupled ocean, atmosphere, and storm structure. To see it, we have to build the hurricane as a heat engine, tilt that engine with wind shear, stack it upright again, and watch a feedback loop close around the eye. The overnight jump starts long before the wind number finally catches up. 30 knots in one day is the operational line. That is roughly 35 miles per hour added to the maximum sustained wind. A storm just below the line may still be dangerous. A storm far above it can cross several familiar categories before the next morning. Typical favorable intensification is slower, often around 10 to 20 knots per day. Rapid intensification sits in the tail of the distribution. It happens in only a small fraction of all observed intensity changes, yet it appears again and again in the strongest storms. The category scale makes the jump look like a staircase. Tropical storm, hurricane, major hurricane, Category 4, Category 5. The atmosphere does not climb stairs. Wind rises continuously, and every category boundary is simply a marker laid across that curve. Intensity is also not the same as size. A compact hurricane can have extreme winds near a tiny eye, while a much larger storm has weaker peak winds spread across a broad area. Rapid intensification measures the peak, not the expanding footprint of every hazard. Forecasters track pressure too, because falling central pressure often accompanies stronger winds. But the relationship depends on storm size, latitude, and background pressure. There is no single pressure value that automatically means one category. The whole circulation matters. This is why the threshold is useful but incomplete. It tells an operations center that the rate of change has become exceptional. It does not say which part of the storm reorganized first, whether the change will continue, or exactly when the acceleration began. For that, start at the surface. A hurricane is not powered by hot water in the way a kettle is powered by a burner. It is powered by a difference between the warm, moist ocean surface and the cooler air high above it. Wind moving across warm water helps evaporate it. The air just above the sea gains water vapor and energy. Near the center, low pressure draws that air inward. Because Earth is rotating, the inflow curves instead of taking a straight path. As the inflow approaches the eye wall, friction slows it and piles it into a narrower ring. The air has nowhere to go but up. Water vapor condenses inside towering thunderstorms, and that phase change releases heat into the storm's core. The warmed air becomes buoyant and rises faster. Near the top of the troposphere, it spreads outward as thin cirrus outflow. A healthy hurricane, therefore, has a vertical circulation, inward near the ocean, upward in the eye wall, and outward high above. Condensation does not create energy from nothing. The ocean supplied the energy when water evaporated. The storm transports it upward and converts part of it into motion. That conversion works best when the thunderstorms surround the center, instead of firing on only one side. Heating the core changes its density and pressure structure. A warmer column occupies more volume, and pressure near the surface can fall. The lower center pressure steepens the pressure gradient between the eye and the surrounding atmosphere. A steeper pressure gradient accelerates the inflow. Faster surface wind increases evaporation and transfers more heat and moisture from the ocean. That supports stronger eye-wall thunderstorms, which can warm the core further. The pieces begin to reinforce one another. This loop is the basic engine, but every tropical storm has some version of it. Rapid intensification needs more than an engine that runs. It needs an engine that loses fewer inputs, exports air efficiently, and organizes its heating close to the center. Sea surface temperature is the obvious fuel gauge. Warm water raises the theoretical ceiling for a storm, yet the temperature of the top millimeter says little about how the ocean responds after hurricane winds start churning it. If the warm layer is deep, mixing brings more warm water upward. If it is shallow, the storm quickly pulls colder water from below and creates its own cool wake. Two patches with the same surface temperature can feed a hurricane very differently. Ocean heat content captures some of that depth. Warm currents and eddies can hold enough energy below the surface that violent mixing fails to cool the water much. Hurricane Michael intensified over high heat content in the Gulf, including the loop current and nearby features. The air matters just as much. A dry middle atmosphere can be mixed into the circulation, evaporate cloud droplets, and weaken thunderstorms. Moist air near the surface helps the storm keep drawing energy upward. Warm water under dry, hostile air is an unfinished recipe. Scientists combine ocean temperature and atmospheric structure into an estimate called potential intensity. Think of it as a ceiling, not a prediction. A high ceiling says strong winds are physically possible. It does not guarantee that the storm can organize well enough to reach them. The storm must pass several gates at once: enough ocean energy, enough moisture, limited disruptive shear, useful outflow, and a core already capable of concentrating heat. A missing gate can hold intensity nearly flat, even while the water remains warm. The gate that most visibly deforms a storm is vertical wind shear. It is the change in wind speed or direction with height. Shear can push the upper circulation away from the low-level center and tip the entire heat engine sideways. Imagine drawing a dot at the center of rotation near the ocean, another halfway up, and a third near the cloud tops. In a strongly sheared storm, those dots do not line up. The vortex is tilted, like a stack of plates sliding apart. Thunderstorms then release much of their heat away from the surface center. The pressure fall is less efficient because the warming is displaced. Dry air can enter the exposed side, while rain and convection cluster downwind of the shear. The low-level circulation may still look organized beneath the clouds. Microwave instruments can reveal curved rain bands, and a small inner structure that ordinary visible imagery partly hides. That buried structure matters because it gives later thunderstorms something coherent to wrap around. When shear relaxes, or when the storm's own circulation becomes strong enough to resist it, the middle and upper centers can move over the low center. Heating becomes more symmetric. Rising air concentrates into a ring instead of continually rebuilding on one side. Symmetry is not just visual polish. It puts latent heating where it can lower central pressure most effectively. It also protects the core from dry environmental air. A slightly better aligned storm can therefore use the same ocean much more efficiently than a tilted neighbor. This is one source of suddenness. Alignment can improve gradually, but its payoff is nonlinear. For hours, convection gets sheared away. Once enough of the vortex stacks, each new burst helps preserve the structure that the next burst needs. The storm has crossed from repeatedly repairing its engine to improving it. Forecast models that begin with a slightly weaker or more tilted core may miss that crossing by several hours, and those hours can separate ordinary strengthening from rapid intensification. Early tropical cyclones often have curved rain bands, but no complete eye wall. Strong thunderstorms pulse in separate clusters. Their small circulations merge, fade, and reform, while the broad center remains exposed or poorly defined. One convective burst can still matter. Rising air stretches the rotating column beneath it and can increase spin close to the center. Several bursts rotating around the same small radius begin to build a more continuous ring of vorticity and heating. As the ring closes, inflowing air is forced upward around more of the center. Gaps that admitted dry air shrink. The pressure field becomes smoother and steeper. Instead of isolated towers borrowing from a loose circulation, the eye wall starts acting as one connected structure. The eye can appear surprisingly late. Air inside the ring sinks and warms, clearing cloud from the center. On satellite imagery, that clearing may look like the moment the hurricane became powerful. Dynamically, it is evidence that the inner core was already organizing underneath. The radius of maximum wind also matters. Air carrying angular momentum inward tends to spin faster as its orbit shrinks. A compact core can concentrate a large pressure change across a short distance, producing extreme peak wind without requiring an enormous storm. Now the pieces lock together. A closed eye wall focuses heating. Focused heating lowers pressure. Lower pressure accelerates inflow. Faster inflow delivers more moisture and angular momentum to the same compact ring. The inner core can spin up much faster than the outer storm changes. This is the structural payoff hidden inside the wind graph. The line does not steepen because the ocean suddenly switched on. It steepens because the storm assembled a more efficient machine around its center. Begin with a small central pressure fall. It increases the force pulling air inward near the surface. The inflow crosses the ocean faster, and stronger wind increases the transfer of sensible heat and water vapor from sea to air. That added energy does not spread evenly across the storm. The closed core channels it toward the eye wall. Thunderstorms there release more latent heat, warming the central column and supporting another pressure fall. At the same time, the circulation gathers angular momentum from a wider area. Friction removes some of it, but a strengthening compact core can still contract the maximum wind inward. The pressure gradient and the shrinking orbit both favor faster wind. Surface flux depends on the difference between the ocean and the near-surface air, plus wind speed. This is why moisture around the storm matters. If the inflowing air is already warm and moist, the engine behaves differently than it does when dry air keeps entering. The eye wall's heating also drives upper-level outflow. Efficient outflow removes mass from the column and helps surface pressure fall. If air cannot escape aloft, rising motion backs up, and the engine loses efficiency. No single arrow in this loop guarantees rapid intensification. The loop accelerates only when enough links strengthen together. Ocean supply, compact inflow, symmetric heating, pressure fall, and outflow have to remain coupled while disruptive processes stay weak. Once coupled, the rate of change can outrun our visual intuition. A modest structural improvement alters the next hour of heating. That alters the next pressure field, which alters the next inflow. The storm is changing the conditions that control how fast it changes. Otis shows this transition with unusual clarity. On October 23rd, convection was still displaced west of the low-level center by easterly shear. Some dry air remained nearby. The storm moved over water around 28 to 29 degrees and strengthened only modestly. Late that day, microwave imagery showed a well-defined low-level structure with a curved convective band. Overnight, the shear weakened somewhat. Otis approached water near 30 to 31 degrees Celsius, roughly 1 to 2 degrees above normal for October. The warm water raised the available energy, but the structural change decided how quickly it could be used. Deep convection wrapped around the center on the morning of October 24th. A mid-level eye appeared, and the inner core solidified. By 1200 UTC, Otis was estimated to have become a hurricane with 65-knot winds. 6 hours later, hurricane hunters found a closed circular eye only about 10 nautical miles across. The eye was warming rapidly, a sign of strong subsidence inside the ring. The aircraft measured the central pressure dropping about 10 millibars between fixes, only 85 minutes apart. Otis likely reached major hurricane intensity that afternoon. Conventional satellite estimates were struggling to keep pace with the compact storm. At 300 UTC on October 25th, Otis reached an estimated 145 knots. The National Hurricane Center report describes a 90-knot increase in 21 hours, second only to Patricia in the Eastern Pacific record. Otis made landfall at Acapulco about 3 hours and 45 minutes later as a Category 5 hurricane. The case is extreme, but its lesson is general. When the inner core closes near land, intensity can change faster than plans built around yesterday's storm. Forecast models never know the exact state of the atmosphere. Satellites see cloud tops well, but the most important early changes may occur under the canopy, inside rain bands, or within a compact core smaller than the spacing of many observations. Aircraft, dropsondes, radar, microwave sensors, buoys, and ocean floats add crucial detail. Still, no observing system measures temperature, moisture, wind, and pressure everywhere at once. A model begins with a best estimate that contains small structural errors. Those errors matter most near a threshold. NOAA researchers tested ensembles of Hurricane Gonzalo by making small changes consistent with observational uncertainty. Simulations with slightly stronger, better aligned initial cores intensified earlier than simulations with weaker, less aligned cores. An ensemble exposes that sensitivity. Some members keep the storm tilted, others close the core and accelerate. The spread is not a collection of competing certainties, it is a map of plausible outcomes produced by uncertainty in the starting storm and its environment. Operational guidance therefore estimates the probability of different intensification amounts over 12, 24, 36, and longer periods. Predictors include recent intensity change, ocean conditions, shear, moisture, potential intensity, and satellite measures of inner core organizations. The hardest question is often not whether the environment becomes favorable, it is when the storm structure takes advantage of it. A forecast can recognize every ingredient and still place core closure 6 hours late. Near a coastline, 6 hours is a large error. Forecasting rapid intensification is a threshold problem inside a partially observed feedback system. That is why probabilities and repeated updates are more honest than a single smooth intensity line. The spread carries information that the center line cannot. Warm deep water, moist air, low shear, and high potential intensity sound like a recipe, but storms often enter favorable environments and strengthen slowly. Ingredients describe what is available. Structure controls whether the storm can combine them before the environment changes again. One storm may have a broad, disorganized center. Thunderstorms keep forming, but they rotate around different points and never close a compact ring. Energy is present, yet heating fails to concentrate where it would produce the largest pressure fall. Another storm may be vertically tilted. Even moderate shear can interact with nearby dry air and create large asymmetries. Convection repeatedly fires down shear, circles the center, and dies before enough of the vortex stacks. A third storm may churn cold water upward. The surface looked favorable before the wind increased, but a shallow, warm layer cannot withstand mixing. The ocean feedback turns negative, just as the atmospheric core tries to organize. This is why two storms in similar maps can behave differently. Their hidden inner cores have histories. Previous convective bursts, eye wall size, vortex tilt, dry air intrusions, and ocean mixing determine how close each storm is to a self-reinforcing state. Near that state, small differences grow. In one model member, the eye closes before shear rises. In another, shear arrives first and disrupts the core. Both outcomes can begin from analyses that look nearly identical at the scale of a forecast map. The useful question is not whether the recipe is complete, it is whether the storm has assembled the mechanism that can use the recipe now. Rapid intensification is an event in structure as much as an event in wind speed. The feedback loop has breaks. A slow-moving storm can stir cold water into the surface and reduce heat flux. A fast storm may cross a cool eddy or shallow shelf. Either change can lower the energy supply beneath the eye wall. Dry air can enter through a weak side of the circulation. Evaporation cools downdrafts, which spread near the surface and interrupt warm inflow. Enough disruption opens gaps in the eye wall and shifts heating away from the center. Increasing wind shear can tilt the vortex again. Upper-level outflow may also become restricted by a nearby weather system. The engine can lose vertical alignment or lose its exhaust path even while the ocean below remains warm. Land removes the ocean's source and adds friction. Rugged terrain can tear apart the low-level circulation quickly, as it did after Otis entered southern Mexico. Yet destructive wind, surge, and rainfall arrive before that weakening can protect the coast. Strong hurricanes can also reorganize internally. A new outer eye wall may form around the original one. The inner eye wall weakens, peak winds can fall for a time, and the wind field often expands. This eye wall replacement cycle is not simple decay. Finally, every environment has a limit. As a storm approaches its potential intensity, further strengthening becomes harder. Ocean cooling, friction, and energy loss through imperfect circulation balance the heat engine's gains. Rapid intensification ends when one or more links stop reinforcing the others. The same systems view that explains acceleration also explains the brakes. No hurricane grows without limit, and no single surface temperature tells us where the limit will appear. Otis did not become Category 5 because one ingredient crossed one magic value. Warm anomalous water, weaker shear, a compact low-level circulation, wrapping convection, a closing inner core, and efficient feedback aligned during a very short approach to land. The ocean set the energy ceiling and supplied moisture. The depth of the warm layer shaped how well that supply survived mixing. The surrounding atmosphere decided whether dry air and shear would interrupt the transfer. Inside the storm, structure controlled the rate. Once the vortex stacked and the eye wall closed, heating concentrated near the center. Pressure fell, inflow accelerated, and the storm improved the engine that was intensifying it. That feedback is why intensity forecasts must stay probabilistic. A low probability is not zero, and a high probability does not promise that the threshold will be crossed. It describes how often plausible versions of the system reach a rapid change. For anyone watching a real storm, the practical signal is repeated official information. The forecast discussion explains confidence and competing factors. Rapid intensification guidance shows the tail risk. Watches and warnings translate the evolving system into decisions for a specific coast. Now return to the first satellite image of Otis. The later Category 5 was not obvious on the surface, but the pieces of a compact engine were moving into place beneath the cloud shield. The wind number was the last part of the transformation to become unmistakable. A hurricane can seem to explode overnight because organization changes what the storm can do with energy it already had. The decisive threshold is not warm water alone. It is the moment the ocean, atmosphere, and inner core begin reinforcing the same accelerating loop.